Hello, everyone. I'd like everyone to remain seated, please, as we're going to start the AI Symposium. Let us now turn our attention to another important topic that AI will play a crucial role in: sustainability. The world faces major challenges in several key areas: healthcare, education, and climate, to name a few. Is AI the solution for sustainability, or is it part of the problem, given its potential for high energy consumption? Our panel of global AI experts have some ideas about the role of AI as a key driver of the fourth industrial revolution. To lead that discussion, I'd like to invite Professor Tim Baldwin to the stage.
Good afternoon, good morning. Thank you, Salem, our amazing MC, for guiding us through the session. This is a bit of a change of pace, I realize, from the graduation ceremony itself, and allow me to add my own personal congratulations to our own amazing class of 2022. So we're having a panel with three true icons of AI on AI and sustainability. So without further ado, allow me to introduce our panelists to the stage, and then I will introduce them formally. So Daniela, Phil, and Eric, if you want to come up. So just to say a bit about the format for the panel, so, Daniela, Eric, and then Phil. Yeah. Eric in the middle, Phil at the end. Yeah, they want you to be matched on that. So let me say a little bit about the format for the panel. Sorry, please be seated. So I will go through and formally introduce each of our panelists in turn, and then invite them to say some opening remarks on the topic of AI and sustainability, and we'll go from there in terms of a discussion between us about the different dimensions of what they discuss and broader issues. So our first panelist is Professor Daniela Russ. Daniela's background is in robotics, mobile computing, and AI. She did her PhD at Cornell. She's currently the Andrew and Emma Viterbi Professor of Electrical Engineering and Computer Science at MIT, in addition to being the director of CSAIL, the Center for the Study of, Director of Computer Science and AI Lab at MIT. She was a MacArthur Fellow in 2002. She's a Fellow of ACM, AAAI, and IEEE, and we're very fortunate at MBZUAI to have her on our board of trustees. So let me hand over to Daniela to make some remarks.
Thank you, Tim. Let me start by saying congratulations, class of 2022. Hello, colleagues and friends. I'm really delighted to be here to kick off our panel with a few words on climate change. So let me start by stating again that climate change represents possibly the greatest threat that humanity has ever faced, and there is no single and simple solution to solve it. Research from the Intergovernmental Panel on Climate Change suggests that human activities have already caused our atmosphere to warm about 1 degree Celsius above pre-industrial levels. And the same body estimates that the number will go up to 1.5 degrees Celsius sometime between 2030 and 2052 if human activity-induced warming continues at the current rate. Now, the timeline should worry us, because according to UN climate change, we must limit warming levels to no more than 2 degrees Celsius to avoid the worst-case scenarios. And even at the 1.5 degree level, we'll start to see sea level rises, extreme temperatures in many regions, heavy precipitation in some regions, drought in others. Now, the Earth has enjoyed a climate of stability for the past 10,000 years, with an average temperature that was just right for humans and for the plants and animals we share the planet with. The stability led to the formation of what we now call civilization. Humans changed their way from nomadic to settled. This period we take for granted, but it has been special and brief. It represents just 6% of the time that humans have been walking on Earth. Today, we assume we have climate stability, but for the past 250 years, humans have emitted so much carbon into the Earth's atmosphere that the global average temperature is now higher than it has been over the past 10,000 years, since the beginning of civilization. If we do not change, the Earth's climate will become unstable again. We already see that happening. We already see the effects. So we're not talking about some distant future. This past summer had some of the hottest months on record. We turn on the news and watch videos of Amazon jungle and Borneo jungle burning. Climate change isn't going to happen. It is happening right now. Now, as scientists, we've long studied climate change and sought to understand its causes. We must realize that climate stability is in grave danger, and we must seek out and implement solutions to go back to stability. This actually means cooling the planet to go to pre-industrial level temperatures. Slowing down the warming is not going to get us back to stability. We are on the cusp of dangerous feedback loops. This means changing the conversation from not warming up by 1.5 degrees Celsius to cooling down by 1 degree Celsius over today's average temperatures. Now, part of the solution is policy, which has been very effective in the past. It has been effective when the UK passed laws to stop deforestation, and also when the world agreed to stop the use of CFCs, which were causing the hole in the ozone layer. But we also have solution-oriented avenues, as some technological and some behavioral changes can make a huge difference. And in fact, great work by Project Drawdown and others is already in place to show how behavioral changes can slow the rate of warming. Now, as an AI scientist, I believe there is great potential for AI technology to make a major difference. With AI, we have extraordinary opportunities to analyze what has happened in the past, what is happening now, and what is going to happen, and what consequences our actions could have. And this is the first step in recovery, understanding what we need to do. And AI can support these questions through the creation of planetary-scale digital twins, rooted in deep climate science models that are trained with detailed data and can enable what-if questions, like what if we were to stop deforestation? What if we could do carbon capture? And what if we were to implement other types of solutions? Now, new innovations can slow the impacts of warming, whether through stopping deforestation, preserving biodiversity, or ensuring there is enough food to go around and food is not wasted. These opportunities, along with planetary-scale climate modeling and planetary-scale digital twins, can give us greater insights. So AI innovations can help us optimize all our activities to slow the impacts of warming, whether through optimizing the electricity cost, making transportation more efficient, preserving biodiversity, or ensuring there is enough food to go around. But to do all that, AI systems consume enormous amounts of energy. Researchers at the University of Massachusetts at Amherst estimated that training a large deep learning model produces 626,000 pounds of carbon dioxide. This is equivalent to the lifetime emissions of 5 cars. And that's just one average model. It cost $4.6 million in energy to train GPT-3. The more pervasive AI becomes, the more of these models will be needed. And I'd like to share this example because it highlights a place where policy action to combat emissions and invest in renewable forms of energy can complement technological improvements. These AI systems are so costly because each one contains hundreds of thousands of neurons, sometimes millions of neurons, and billions of interconnections. If we can develop simpler models, this can drastically reduce the carbon footprint of AI. And this isn't a hypothetical. It's an area where AI researchers are already making progress. At MIT and in other forward-looking laboratories around the world, researchers are developing alternative models for AI that are more sustainable. In my group, for instance, we are developing what we call liquid networks, which are orders of magnitude smaller and faster than deep neural networks. They're also robust, causal, and explainable, and can be used in applications with time series data. Now, in addition to using AI tools for modeling optimization and prediction, there is also opportunity to address some of the underlying causes of climate change. For example, an industrial greenhouse in Zurich is pumping in carbon dioxide using the world's first commercial direct air capture plant. The CO2 boosts plant yields and extracts around 900 tons of CO2 a year from the air. Also, Silicon Valley startup Blue Planet employs a chemical process to capture the carbon dioxide from the atmosphere and turn it into pellets that can be integrated in cement for construction. And two London-based architects have developed algae-filled plastic curtains designed to help purify dirty air. Now, the curtains they draped over Dublin Castle in Ireland can suck more than 2 pounds of carbon dioxide from the air each day. Now, it would take a lot of curtains and a lot of buildings to capture enough CO2 to solve climate change, but I believe it's the sum of all these efforts that will make the difference. If we, as a scientific community, choose to focus our energy and investments in this area, I believe that we have the power to slow and even reverse the damage we have done to our climate and our planet. And we know that change can happen, because it was only a few dozen years ago that scientists discovered the hole in the ozone layer. But with global efforts to eliminate the use of chlorofluorocarbons, also known as CFCs, we were able to reverse those trends. And recently, scientists from MIT have found signs that the Antarctic ozone hole has shrunk by more than 4 million square kilometers. That is extraordinary. Now, skeptics may not believe that we can reverse the global warming trends. But then many didn't believe we'd ever walk on the moon. Skepticism has never stopped scientists and engineers from doing the impossible. So I say, let's embrace the challenge of getting back to a stable climate by understanding first and then implementing what it takes to cool the planet to pre-industrial levels, what it takes to clean up the air, the water, and the land.
Thank you, Danielle. We had some very powerful words framing the issue, but also talking about possible opportunities as well as contributors on the part of AI. So I'd next like to go to the furthest end, to Phil Blunsom. So Phil's background is in NLP. He was one of the true pioneers of what we now take for granted in terms of deep learning in NLP. He did his PhD at Melbourne University. He's now a professor at Oxford, in addition to being the chief scientist at Cohere.AI, after stepping down as the NLP lead at Google DeepMind very recently, last year. So, Phil.
Thank you, Tim. And thank you for inviting me to this event, and congratulations to all of those who are graduating. It's an amazing time to be embarking on a career in artificial intelligence and machine learning. There's so many exciting things happening. What Tim didn't mention is I was actually his first PhD student about 20 years ago. So I have a connection with many of you students in that. In those 20 years, the field that I've worked in, NLP, AI, machine learning, has changed beyond recognition. We used to spend whole PhDs careers just engineering models to do very specific tasks, like just being able to extract a name from a document. We'd build a whole system with an intricate structure to do that. Today, we see systems based on what we call language models that we can just write a description of the task we want it to do, take this call transcript, extract all of the events, list them in bullet point form, and the system will do that for you. No more building models for specific tasks, we just have to write what we want. So as I said, this has been enabled by something called language modeling, a technology I've worked on throughout my career. A very obscure technology mostly. It's the idea of assigning probabilities to bits of language. But today you see it on the front page of major newspapers like the New York Times and the Guardian because of things like ChatGPT that some of you may have seen and other demos of this sort of technology. And what we're seeing is based on something that we've come to refer to as large language models, which have also become the poster child for inefficiencies in AI and energy use. And GPT-3 is a case of that Daniela referred to. So these models are trained on a huge amount of data. An average big language model like the ones, so I'm a chief scientist at a company that builds such models. We might train a model for roughly 2 months on maybe half an exaflop of computation, and that's a lot of energy usage. But if we were having this discussion maybe a year ago, we'd be talking about the increasing size of models. They're getting bigger, 300 billion parameters, 500 billion parameters, and where will that stop, and all the energy usage. But a lot has changed. Models are actually getting smaller. So as we've moved out of the research lab where people are just trying to make a headline and get a good result in a research paper, as we've commercialized these models, the energy uses start to constrain us and the cost. And the models are getting smaller and more efficient. So this process is starting to drive what we're doing. We're also shifting from this idea of relying entirely on these big trained models to refining them with this idea of supervised training or reinforcement learning. And this is the idea that we use a small amount of data to significantly improve the performance of the models in these tasks. And that ability to give an instruction to a model is an example. And now this sort of training is orders of magnitude more efficient than the pre-training we've done in the past. So whereas we might have spent 2 months and a huge amount of energy training a big language model, once we've got that, we can reuse it in different ways, and the supervised training might take a day on 1/10 of the computation. So we're seeing this trend towards smaller, faster computation. A lot of that's driven by the performance, and a lot of it's driven by the energy costs. So the other thing that's happening as we go from research-driven development of these models, that it has been largely sponsored by big tech companies that haven't been terribly constrained by the cost of what they're doing, into the commercialization, which is a lot being led by smaller companies and startups. We're transitioning from worrying as much about the training costs and the efficiency of these models into what we call the inference or deployment, so how we actually use them. So we might train the model, but then put it online and people use it, and that has a cost. Now, if you think about, many of you might have seen ChatGPT, the sort of numbers of users that system has been getting, the cost of computation, if you stretch that out over about a year, it probably comes to about $1 billion worth of computation. And that's a lot for a system that's free. And that's not something that's easy to sustain. That's compared to the actual supervised fine-tuning, which is probably significantly less than $1 million. So while the focus on efficiency in these big AI systems has been about training, we're rapidly moving to this, this world where efficiencies are really about how we deploy these models. And that's really following trends of other similar technologies like search engines and Google, where the cost of building the index is dwarfed by the cost of serving customers. So yes, cost is what is currently driving and constraining efficiency. And as companies deploy these models, those costs are what driving the innovation that's bringing down the efficiency of these models. Of course, we're always pushing up against those limits. Now, one of the advantages of the way these AI models work is that the energy use gets centralized in a data center, in the data centers of big tech companies. And if you can reduce the carbon footprint of those data centers, you can reduce the carbon footprint of the technologies. And you'll see a lot of big tech companies proudly claiming that they're carbon neutral because their data center is powered by a hydro plant or something like that. Of course, when a big tech company comes along and buys up all of the hydro power, it displaces all of the other users of that. And so it's not really terribly carbon neutral. So the decarbonizing of these big AI technologies is really linked to the decarbonizing of our society in general and our ability to decarbonize our energy systems. I'll just finally say for those students, new graduates, that there are huge opportunities in the way we develop models, the technologies we're using. The poster child of big language modeling and many other technologies like protein folding is the transformer. Many of you may have heard of this technology that was developed at Google. It's incredibly inefficient. It's incredibly efficient to train with, incredibly inefficient to deploy with. So there's a huge amount of interest in what comes after the transformer. What's a model that you can actually deploy efficiently? So I will leave the students with that thought as something to ponder and pursue. And thank you again.
Thank you, Phil. So our final panelist needs no introduction in this forum, of course. Our own president and university professor, Eric Xing. Just very briefly, Eric actually did 2 PhDs in computational biology and then machine learning at Rochester and then Berkeley, respectively, and has been with us at MBZUAI for the last 2 years, leading us very ably. So, Eric.
Thank you very much. I want to again, congratulate our 2022 graduates, for achieving such a remarkable milestone in your career. And in fact, I think you are, as Dr. Tang just mentioned, you are graduating at the right moment from the right place, and also in the right track, because sustainability is going to be the topic in the next decade, I believe, in all dimensions. So to follow that kind of motivation, maybe I want to continue with the great, opening from Daniela and Phil, on, how AI connects to sustainability, and maybe add a little bit more dimensions into how I see, the connection between AI and the sustainability, right? So typically, I think AI could be viewed as influencers, in sustainability, in at least the three following ways. The first, obviously, is that AI is a tool. It is a tool for decision making and hopefully for better decision making. And in our business of sustainability, energy, for example, agriculture, where you plant and how do you plant, and how do you organize logistics for ports and so forth. When you use AI, you hope that it can make a better decision than human being, because the AI tools are trained on larger amount of data, are doing quick and hopefully powerful mathematical calculation, in a way that is beyond what human being is achieved. It's just like you play with a Go player. Nowadays, you go to an AI player, instead of a human player, if you really want to win the game. So that's actually an important dimension we shouldn't forget. AI is a tool that can be deployed in many sectors to hopefully find the best way to reduce greenhouse emission, to do better planning, to reduce cost, and also to maybe increase efficiency. That itself is already a big addition, into the containment, of pollutions, of extending sustainability. And then the second area, as both Phil and Daniela also mentioned, is that AI itself is a consumer of resource. Therefore, it automatically, connects to, how to make the AI practice itself more sustainable. Because, as mentioned earlier, training larger AI models these days is a very trendy thing to do. But what is not really highlighted is the energy footprint and also many other consumptions, including people, and manpower and logistics and other resources that are consumed by AI. I think there are a lot of researchers now already becoming aware of this challenge and opportunity. And there are, areas where people can work on algorithms and theories and the models to make, for example, the larger AI model smaller and smarter, more efficient, so that in achieving the same goal or maybe a better goal, you make use of less computational power. But also, it's actually quite interesting to relook, some of the old fields in computer science, such as operating system, programming language, and these areas actually were originally, built to actually help people, to build, a better computing infrastructure, better language, and also turn the code more efficiently. I think this may be another, an opportunity we may want to explore here at MBZUAI or, in some of the new programs that we are building, to really, open up, new opportunities for established and mature fields, for this potentially new potential to be unlocked. But another dimension I do want to emphasize, which I found to be very strongly these days, is the impact of AI on human society and on human civilization. Because we human beings need to also be sustainable, right? For example, we need to be healthy, we need to live long enough to get the work done. And also the society need to have enough creativity and brain power to further, the science, to further the curiosity, and also to make, new innovations, and also to solve future problems. And I think there is a challenge here. For example, with the deployments of tools like ChatGPT, you can use it in very different ways. You could, for example, use it as a tool to get your work done better, and also allowing you to make more efficient use of your time to do something that is not doable by these AI tools. But on the other hand, you could also use it, you can rely on it to get to do your work and retire yourself from your work, and then become, very soon maybe obsolete, for the very occupation that you are occupying, right? So that's actually, in my opinion, could lead to a unsustainable human and machine relationship, because if you don't practice and you don't work for a certain period of time, you may lose your skill, and your brain may stop becoming innovative and curious. So that's actually a dimension. I don't know, it's really relates to the technology itself or the culture and the policy that we should look into, and also the ethic issue that we should look into relating to AI. And also don't forget that training every one of these larger models require data. There is also a data sustainability issue. In the past, we often say that the model and the infrastructure and the hardware are lagging behind data. But now I'm actually even augmenting or maybe revising my own conclusion. I found that the models are perhaps outpacing the data. And I still see an opportunity or maybe even a danger that some years in the future, our universe may be filled with artificially produced data. And then, imagine this data go back to the model, and you start kind of a closed loop of a model consuming its own product. And that also makes the AI productivity and innovation becoming unsustainable. So I want to just leave a few questions to here, and hopefully elicit provoke some great thoughts, from our experts in here to see how can we together work on these challenges.
Thank you. So I now have the unenviable task of trying to construct questions about all these things. My first question, which came up from each of you, was this tension, so that the raw cost of whether it's large language models in NLP or models in CV, it's a fairly pervasive trend. More recently, protein folding, as Phil mentioned. There's a tension in terms of yes, we now know how to train these models much more efficiently, but to get there, we had to splurge in terms of our computational investment, in terms of trialing ever larger models, learning about model distillation, developing more data-efficient methods on the basis of that. So that tension, is there a way around it? Are we more savvy now that we don't have to sort of splurge and then trim back and emerge as sort of being more sustainable, but after a sort of period of 5 years in NLP of kind of breaking the bank? But is that even responsible? As AI researchers, is that something that we should be doing? Should we be turning our backs on that sort of culture? So perhaps starting out with Daniela.
Well, so that's the big question, Tim. And the way I see it, we have models that, and we have AI approaches that work well, and we're putting more and more data into them, and we're making them bigger and bigger, because then they work better and better, right? So, in fact, it's important to realize that the greatest advances that we have today are due to decades-old technologies that are enhanced by computation and data. And these technologies have limitations. The reason we make them bigger and bigger is because we actually don't understand how they work. But it just seems that the more that they do well within, let's say, the convex hull of the input that they are given. So the more input we give them, then the better they are going to be. But we still don't have any proof, any evidence that that the models will do well. Yet they do so much. We have so much benefit. And so my idea is that we really need to do two things. We need to really better understand today's methods. We need to understand why they need the huge amounts of data that they need, why they end up being so big, why they're not explainable, why they're not causal, why they're not robust. How can we actually understand the existing state of the art and make it better? But I also want to observe that if we stick to the current path and we don't do anything different, then more and more people are going to be doing the same thing, and the results are going to turn increasingly incremental. And so it's also important to to stretch ourselves. It's important to ask ourselves, what is there beyond deep learning? How can we come up with other models, with other ways of seeing the problem that perhaps provide us with more benefits? So since I'm a roboticist, I will say that the physical world is very important in how we think about it. And so we have a lot of knowledge of physical models that have been developed by science over hundreds of years. And I think it's interesting to think about some way of connecting the model-based approaches with the data-based approaches to get to different solutions, to get to solutions that somehow capture the best of both worlds. Eric, what do you think?
I cannot agree more.
Thank you.
Yeah, I think Daniela really point to a very, very important point that these models needs to be understood more deeply, to the point that we need to understand its potential, but also its limitation. And also, I want to add that maybe we human beings need to also think more actively about the new problems, and also to think about what are those opportunities and problems that the machine currently we have, or maybe in the future, cannot do, so that we position our energy to the right direction. And in that way, hopefully, new opportunities and also the civilization can move further. I think every tools eventually, we build will do better than human. That's because that's the reason we build it. Otherwise, we wouldn't build a tool that is worse than human being, right? But we're not building tools to replace human in every dimension, but in certain dimension. That's why also, we still, do exercise. And we have Olympia, even though all this machinery can run faster than human, and all this machinery can be more strong than human, right?
But can I say something?
Yeah.
Yeah. Okay. I'm going to say something to that Phil might not like, but I'm just going to say that I've been kind of fascinated by ChatGPT, like everyone else. It's amazing how it produces code, it produces text. But then if I say, tell me about Daniela Rus, ChatGPT will get my bachelor's degree wrong. It will say I'm a professor at Carnegie Mellon, which I'm
really?
not. So it still makes mistakes.
It will get it right tomorrow.
So,
once I hear that.
So it still makes mistakes, and it's really, there's no semantics in what comes out of ChatGPT. I don't see it ready to replace our tasks. I see it as a way of, as a kind of almost like an assistant, like an intern that gives you some suggestions, but you have to go and check them out because it's not clear that what comes out of it is correct.
Yeah. I want to add, so maybe Phil will also add to that. I will soon give you the mic.
Okay.
But just to follow up what Daniela just said, I think, upon kind of a notification and upon further training, they will get it right, in certain well-defined tasks. But there are many other tasks where I think a human being shouldn't be competing with, for example, the ChatGPT. For example, in one problem we do with protein structure prediction, we know that the AlphaFold2 and also its relatives are now making amazing predictions. They predict about 200 million structures, everything basically, in the protein database in 2 years, whereas the entire 50 years of structural biology produced about 200,000 structures, right? So in that sense, I'm fine to eliminate that field of structural biology and focus on redeposit the money into another direction, for example, better trial system and the better animal models to test diseases. I think the machine, and the human being really can be complementary rather than, be really competing with each other. That's kind of how I see the sustainability can go longer, because with the machine, our energy can be saved for something even more fun and maybe more interesting. Okay, now you.
Thank you. I think Daniela's example of the issues with knowledge and factuality in big language models is a good example of efficiency, because this is really a case of a very inefficient way of learning knowledge. What we're doing is we're taking the whole of the web, training big models over a very long period of time on this, and hoping that all of that knowledge ends up in the weights of the model. And one, that's a very blurry way of representing knowledge. Two, if anything changes in the world, then you have to retrain your big expensive model, which is not good. So it's a great example of how can we do that, the question of how can we do that more efficiently. And there are lots of great modeling ideas for that. And the obvious one is what's called the retrieval augmented generation approach, which means saying, rather than trying to cram all of the knowledge into these big models, why not just enable them to access knowledge, a bit like a human, use the search engine, look at the data, and that's what we'll see ChatGPT doing next. I'm willing to bet in a few months you'll see it augmented with a retrieval system, and so it can access your web page, bring that data down, and condition on it directly when it generates. It won't get rid of all of those errors, but it will get rid of a lot. But it's also massively more efficient than having to, because then you can train a much smaller model that just deals with the basics of language and leave all of the sort of knowledge of the world to the same way humans do. We don't hold all of this in our head, we access it.
But it's still pattern matching, it's not semantics.
Well, I mean, you can have a lot of arguments about semantics, and I would say, maybe with a nod to Tim, that the lexical semantics of a ChatGPT is pretty amazing. The compositional semantics is still pretty questionable. So we're going sort of slowly up the semantic hierarchy, and there's definitely semantics in there. But I wouldn't necessarily say it's pattern matching either. There's a generalization in there, but it's not compositional semantics in a human way, in any sense. Maybe just coming back to the sort of efficiency question, what Tim raised with training of models. What I would say, when we talk about efficiency of training models, we think of these sort of how many flops it takes to train a model of a certain size. It never actually works out that way when you train big models. There's still as much art as science. You don't just turn them loose for 2 months and come back and it's done. Engineers have to babysit them all of the way. They break. Our unnamed hardware provider, I would estimate, our systems crash maybe twice a day on the big models, and that's because we're training on many thousands of devices at the same time, and any one goes down, it kills the whole thing. This is extremely inefficient. So besides the actual efficiency of the model, all of that hardware crashing, models diverging, having to retry and experiment to get a run done adds multiples to the actual cost and energy usage of a model. Improving any of that, research that just works out how do we get a model to not diverge constantly, how do we have hardware that's actually reliable, has a huge impact on efficiency beyond models. And just also a final different way of thinking about this, in the way the company I work for provisions hardware, we pay for hardware on a multiple-year contract, and we have a set amount of hardware. If we don't use it, we lose it in the computation. So I will constantly go, and probably after this, go back and look at our utilization of the hardware, and if it's below 80%, I'll start sending messages to engineers saying, why aren't you running experiments and training our models? So within all of the training of models and such going on, you can really just look at the hardware and say, if we build this hardware, we're going to use it at about 80% for this amount of time, and we have to make the energy usage of that as efficient as possible if we really want to bring down the impact from things like carbon and such.
So I want to take a different tack next and pick up on some of your comments, Daniela, about not so much the sustainability of AI as AI for sustainability. Particularly for our graduating students or a largely AI audience, I suspect there are a lot of people who are sort of feeling that, yes, it's such a critical issue, but what can I do? What are the steps that I can take personally using my AI skills? Who should I work with? What data should I be trying to use? How do I make a difference? Do you have any suggestions or advice?
Well, let's see. So I'm very excited about the idea of a planetary scale digital twin. That is really rooted in all the right models. This will be very complex. It doesn't exist. But it's the kind of thing that we could imagine creating. And if we were to get it all organized, then we would be able to run what-if scenarios. So what would we need for such a complex digital twin? Well, we would need the models for everything that is happening on the planet. It's very complicated. There's a lot of complexity there. Then we would need to use current data to train the models so that they are accurate. And then if we get to this place, we can begin to ask what-if scenarios. Then we can see how various actions and activities and behavioral changes will have an impact. And we can perhaps instantiate this digital twin for different parts of the world because there are different phenomena in different parts of the world. But nevertheless, we have to link everything because our planet is a very complex linked feedback system. Aside from that, I would recommend to everyone a book called Project Drawdown. So Project Drawdown is really extraordinary. It's a group of scientists that have been studying 100 human behaviors and industries. How we used to do things and how we could do them, how much it would cost, and how much CO2 emissions we would save. It's really extraordinary because for every kind of human activity, you actually see in a quantitative way how making a change will actually make a difference. And so I think that this is really something that is like a kind of a wake-up call but it's in some sense a measurable way of saying, hey, change this, change that, and you will make an impact. And the third thing I will say is that we really have to start cleaning up. We have to really look into how we can use robots and the AI to begin to decarbonize, to begin to clean our air, to clean our waters, and to clean our soil. We can continue to optimize what we do, but in parallel with that, we really have to clean up.
Eric or Phil, do you have any ideas?
As a NLP researcher, we don't tend to directly work on the application of that to sustainability, but the most obvious one is information access. The more we can make information available and the ability to bring together different sorts of information, the greater chance there is of making progress. So that's both, there's great progress being made in the ability to search and integrate sort of scientific information, because there's so much being published on these topics, it's often hard to bring it together and see where the opportunities are. So I think NLP has a role in that, largely in the understanding and information fusion.
Maybe I'd like to remark on what can be done in 2 dimensions. One is about the exciting problems that AI can be used to work on. Especially in the space where humans are not doing such a great job. I mentioned about already drug design and the biology, but also in agriculture. Even in oil drilling. In energy transportation, climate, in the weather prediction. Clean up all the pollutions and other things that produced from a human being and so forth. I think AI can really give us a more optimal and a more holistic planning and action path toward that. So I encourage as a university administrator, I really would like to see faculty and students choose to work on those topics. But secondly, I want to also comment on, as a computer scientist, the methodology opportunity that we may be facing. This is also a sustainability problem itself, because it is the sustainability of a human capital. Look at the problems that we're talking about these days, large language models, big data. It looks like they all belong to big industries, and they define a topic, and we work on prompts, and we work on fine-tuning and other things to be almost like a parasite sitting on that. But what if suddenly GPT-3 becomes GPT-4? What does it mean? Or maybe once for all, that model structure was altered, and then all your prompts and your RL algorithms stop working. That's actually a real challenge, because we academics start to lose that kind of edge and also the intellectual leadership, in directing and guiding the science itself. So I think there are opportunities and research topics outside of the large models that is heavily, infrastructure and data dependent. That actually we university researchers and academics could also work on. So this is something I really want to advocate. I'm worried about in the current research conferences. Over 90% of the papers are really focusing on building on existing bigger models and the bigger data infrastructure to work on very incremental problems. There are actually more problems out there and more methodological space out there to be explored. For example, I can name quite a few, right? For example, uncertainty quantification of every method that I develop does not need a larger model. You need to have the right mathematics and also the right inferential technique to work on. Strategic games and also mechanism design is another space where you don't also need larger models, but you need to have a lesser assumption kind of a problem space where you don't assume that you only have one agent but multiple agents, each of them using, for example, a NLP model or a CV model to communicate. So there are a greater space of research where I see, by and large, still vacant, for we academic people, to actively jump in, because it is very high risk. It is not necessarily leading to very fast publication and many publications. It requires many years of investments. But in my opinion, these are exactly where you'll find sustainable research and also a sustainable brain that you can always become very active and hopefully become more and more competent to push the boundary even further instead of following these big industrial trends of jumping into some low-hanging fruits.
We're out of time, strictly speaking, but today is all about our graduating students. So to finish up, I wondered if each of you had any quick comments addressed to our graduating students and sort of the upcoming generation of AIs in terms of a general advice going out into the world as AI practitioners. Daniela, putting you on the spot.
Right, so my general advice to the graduates is to find your passion and engage in purposeful, meaningful work. And remember that every day that goes by is a day you will no longer have, so make the most of it.
Wonderful. Phil?
I'd firstly say it's a very exciting time to be embarking on a journey in AI. It may look that a lot has been solved, but it really hasn't. Really, we're just seeing how much there still is to do. There's so many things to solve. So there's a huge amount for you to go out and study and research. If you do follow a career in research, really try to follow hypothesis-driven research. Don't get distracted by the latest things on Twitter or what the big tech companies are doing. Really think about what is the question you're interested in asking, and seek answers.
Fantastic. And the last word
I said it
from
up
Eric.
today already, but I can still add two more. I think my two sentences for you. One is stay very close to the real-world problem and own it. And secondly, keep learning, because the world is evolving, problems are evolving, knowledge are evolving. You actually can only become relevant and useful if you have a very, very open mind that keeps you, keep you learning, continuously.
Fantastic. Please join me in thanking our amazing panelists for a great event. That concludes things. Please join us coming out into the foyer and celebrating the hat tossing of our graduating class.